seen me in such fine quality chemistry, educational videos such as oxidation reduction. Without it, you wouldn't live. And redox, redox, redox is here. Okay, so today what we're going to look at, the first part of looking at redox reactions. I did make video tapes on how to do balanced redox equations in acid and how to balance redox equations in base, but those are two separate other videos which you can catch the absolute action on those. Today I want to look at oxidation numbers, okay? And how can we tell if an oxidation or reduction is occurring in a reaction? Well, if I've got the time. But I want to look at oxidation numbers because that's a key thing. In chemistry, you have those atoms that they are going to have an oxidation number. Well, what do we mean by that? Well, an atom could be neutral, okay, or it could lose electrons or pick up electrons. If it loses electrons, then it becomes oxidized and it begins to have a positive charge. On the other hand, if it picks up electrons, then we say it's reduced and it becomes going from positive, it goes towards zero. If you pick up more electrons, it can go into the negative zone. But anyways, what we need to do is look at some of the basic rules on how to assign the oxidation numbers. So the first thing is, the first rule, the oxidation number of any pure element is zero. So if we look at something like gold by itself or sodium by itself, it's zero. You'd say, but wait a minute, Canu, sodium is a +1. Well, remember, in its natural setting, the sodium is going to have all its electrons, so it's going to have a charge of 0. Now, is it going to stay that way? That's another issue, okay? We're not talking about what does it take to make the atom have its maximum amount of valence electrons. That's not what we're talking about. We're just talking about the element in its natural state is going to be 0, a pure element. So the oxidation number of H and H2, for example, is going to be 0. The oxidation number for silver will be 0 when it's in its pure form. Now, how do we see this in a reaction? Well, typically, so for example, we can look at AgS. When we look at that in an equation, okay, that has an oxidation number of 0. Now, if it loses an electron, then yeah, the Ag becomes a +1, which is that's its typical oxidative state. But remember, when it's a pure element by itself, it's going to be a 0. Now, does that have anything to do with its stability? No, it doesn't. If we look at sodium, we know that sodium is unstable by itself. It has to be kept in kerosene. But the reality is that sodium does have a 0 oxidative state. That's a 0 charge. It's neutral. So, now with that, let's move on to the next one. The oxidation number of a monatomic ion. Well, what do we mean by monatomic? One atom ion is equal to its charge. Okay, so if a monatomic ion, like sodium for example, it has a +1, that's the oxidation number for the sodium. The oxidation number of chlorine in the Cl, the chloride ion, the Cl-1, is a -1. If we look at magnesium with a +2 charge, guess what? That's its oxidation number. Okay? So an oxidation number, it could be 0, it could be positive, or it could be negative. It depends on the individual element itself. When the element is pure by itself, then it's going to have a charge of 0 based off of this. Okay? But if it's a monatomic ion, it's going to be equal to the charge that it has. So for oxygen, okay, oxygen ion, it's going to be a -2.
Now the third one here is the sum of the oxidation numbers in a compound is 0 if it's neutral. Well, that makes sense because if it's positive or negative, that means it's going to react with something. If it's neutral, it's going to be less likely to react with something. Does that necessarily make it stable? That's not the issue. The issue is, what's the oxidation number? If it's 0, it's neutral. Or equal, so the sum of the oxidation numbers in a compound is 0 if neutral, or equal to the charge of an ion. So we can look at something like NO3, for example. Now, that has a -1 charge to it. Is it neutral? No, it's not. But when we look at something like CO2, now CO2 has no charge to it. It's a neutral. If we look at CO3, it has a -2 charge to it. Well, wait, what's the difference between CO2 and CO3? Well, remember, CO3 has an extra oxygen connected to that molecule. Okay, and as a result, the oxygen brings in an extra -2 charge. That's why we have the -2 charge in there. And again, will it go and hook up? Will it connect with other atoms? Yeah, over time. Okay, let's move on. The oxidation number of alkali metals. Wait, what are the alkali metals? You've got to go back to the periodic chart. Whoops. Now I got it. Here's your alkali metals right here. Lithium, sodium, potassium. Those are your big ones. Cesium, francium, rubidium. All those are +1. Okay, hydrogen, yes, it's in the same column, but it is in its own category. It's special. Now here, the next group, that's the alkali earth metals. Those are +2s automatically. And that's always useful when you're looking for oxidation states of different elements. Okay, so the oxidation number of alkali metals in compounds is +1. And that of alkali earth metals is +2. This is your alkali metals. This is your alkali earth metals right here. Alkali metals, alkali earth metals. Okay? And the oxidation number of F, fluorine, is always going to be a -1 in all of its compounds. That's because fluorine is the most electronegative. That's why. Okay. Let's move on. The oxidation number of H is +1 in most compounds. Okay. The exceptions are H2 because it's found in its natural state, which is H2. The charge will be 0. And the ionic hydrides like NaH or lithium hydride, which you could find in batteries, I believe, the H is going to be a -1 charge to it. Okay? So, usually H is a +1. Unless it's connected to some kind of a metal. Then it becomes a metal hydride and that changes it. Okay, nasty stuff. The oxidation number of oxygen, or O, is -2 in most compounds. Now the exceptions is if you find O2, that's because it's in its natural state. Remember when we go back up here in this first rule, so that's going to be a 0. Now if you have peroxides, like H2O2 or Na2O2, the oxygen has a -1 charge. Now, really, that's the exception rather than the rule. Okay? It's a tricky one, and I wouldn't be emphasizing a whole lot on that. In other elements, you can usually use rule number 3 to solve for the unknown oxidation number. What is rule number 3? That's right here. The sum of the oxidation numbers in a compound is 0 if it's neutral, or it's equal to the charge if it is an ion. Like these. Okay, great. We went over the rules. Now let's talk a little bit about how do we apply them. Well, our next trick, guys, is we're going to be looking at oxidation numbers. So let's look at HNO3. So we're going to find out what's the charge on the H, what's the charge on the nitrogen, and what's the charge in the oxygen, each individual. Now, the first thing you would need to look at is, what's the total charge? If you notice, there's no number up here. If you see a number here, like a 2, does the coefficient affect the oxidation states of these individual atoms? And the answer is no, it doesn't. Remember, all the coefficient tells us is the ratio, how many we have. And at that point, it's like, I don't care how many we have. I need to understand how this is being put together. So let's go with it. If my total charge is 0, okay, because they're not going to put a 0, it's going to be a total charge of 0. I got 3 oxygens, so let's see. According to the rules, each oxygen is a -2, so that's going to be 3 times -2. All right, the nitrogen, well, that's going to be an X because we don't know what it is. And then the hydrogen, well, what do we know about the hydrogen? It's a +1 charge. It's not connected to a metal, so it's not a metal hydride, so it's a 1. So what am I doing? I'm forming an algebra expression here. Ah, he's using algebra in chemistry. Yes, yes, we are. Okay, now the total charge is going to be a 0 because remember, this is neutral. We don't care about this number, the coefficient. Let's look at this. So 1 plus x plus a -6, so 1 plus x plus a -6 equals 0. So let's combine. So x plus -5, because remember I'm going to add the 1 to the -6 is equal to 0. Therefore, x is equal to 5. So what did I get here, boys and girls? Well, I found hydrogen is a +1 charge. I found that nitrogen is a +5 charge. And how about the oxygen? Well, the oxygen's a -2 charge. These are the oxidation numbers of those individual numbers. Now, they're either going to be 0, it's going to be a negative number, or a positive number. Wow, a lot of great choices, huh? Okay, let's go ahead and let's work on another one. Let's see. Let's go with H2SO4. That's a little bit juicy. So here we have hydrogen. Here we have sulfur. Here we have oxygen. What's the total charge on the H2SO4? I'll let you think about it while I go get a drink. And I'm back. Well, the total charge here is 0. There's no number written up there, so that's a 0. So let's see now. I have, what would be the individual charge, the individual oxidation number of hydrogen? It's a +1, so it's going to be 2 times a +1 plus, well, S we don't know, it's X, plus, what do we know about the oxygen? Well, each oxygen is a -2 charge. The oxygen is not a peroxide, so it's a -2, okay? So that would be -2 multiplied by 4, and the whole thing is going to equal 0. So I'm just taking these and then putting them in order. So if we look at this, this is our hydrogen, this is our 2 hydrogens, right? This is our H2, this is our S, and here's our O4. Okay, so let's go ahead and let's work with, okay, so I've got 2 plus x plus -8 equals 0. So let's combine. So x plus -6 is equal to 0. Therefore, x will equal +6. So I showed you step by step the algebra, how to do that. So let's take a look. In hydrogen, we got a +1. The oxygen's a -2. And now, because you see, we knew this, and we knew this because of our rules. They were pretty much fixed, right? So we had to figure out S, and we went through, did the algebra expressions, and S has a +6 process. It's now +6. So, yay, we're doing great on this. All right, let's go ahead. Let's do one more for the sake of argument. HNaCO3, baking soda. Good old baking soda. So here we've got 4. We've got H, we've got Na, we've got C, and we've got O here. All right. What's the total charge on our HNaCO3? Zero. Yeah, there's no charge up here, right? So it's 0. They're not going to write 0 because it kind of looks lame, okay? So we have to assume it's 0. So H for here, well, it's a +1. Why do we know that's a +1? It's not connected, it's not a metal hydride because it's connected to the centerpiece, which is the carbon. So that's fine. The Na, we also know that's a +1. Well, how do we know that? It's not occurring in its pure form. It is also on the first group right here, our first column. Okay, this is our alkali metals, so it's a +1 automatically. Now the oxygen, we know the oxygen is going to be a -2 charge to it. How do we know? It's not a peroxide, and it's not occurring O2 pure in the environment. It's not. It's connected to the carbon. It's got a -2 charge. So let's look at this. I have here, I have 1 + 1 plus X plus 3 times a -2, and that equals 0. So let's look at it again. I represent the H, I represented the Na, I represented the carbon, and I represented the O. That's what I did. So in this case here, ladies and gentlemen, I've got 1 + 1 plus X plus a -6. So let's go ahead, let's combine these, and we're going to say 2 plus X plus a -6 equals 0. So combine the 2 with the -6, we'll say that X plus -4 equals 0. Therefore, X is equal to +4, and that's how we figure out our oxidation number here. So hydrogen's a +1, sodium is a +1, carbon is a +4, and the oxygen is a -2. That's it. That's how we go about finding the oxidation numbers here on this. Hey, I hope that this video has been helpful to you. At this point now, I'm going to be signing off. I'm afraid there'll be no yelling or goodbyes or anything like that. I'm just going to sign off, and that's it.